So we've built up these ideas about linear algebra on vectors and things that we can write out a finite list of coordinates for. Now we're going to take that same toolkit but talk about a vector space made not out of traditional vectors but functions. And instead of dealing with the whole space of all the possible functions, we're going to narrow in. And we are going to talk about a line from A to B where whatever our function does, we start at 0 and we end at 0. And this is going to be a lot more manageable for linear algebra analysis. So this could represent a wave on a string. This could represent a particle in an infinite square well bouncing back and forth between two walls. This could be a periodic function that's going to repeat over and over on the AB interval. And this is just the only interval we need to look at. And this restriction of functions forms a vector space. If the function is 0 at A and 0 at B, and if I get another function that's 0 at A and 0 at B, this still holds true when I add my functions together. It also still holds true if I multiply both sides by a coefficient. Coefficient times 0 is 0. So all the linear algebra rules that I developed for vectors are going to apply to these kinds of functions. But simply saying that it is possible for me to do linear algebra on these is not very illuminating. If I'm going to get into linear algebra, it's helpful to talk about a basis. And it is not clear at all what a useful basis would be. Or for that matter, how we'd get coordinates. If we have a basis, we can get coordinates in that basis through something like, if we want the x coordinate, we dot product v with the x unit vector. And we would like to develop this for our functions. So let's walk through what I just did here very, very carefully and see what all of the essential steps are to make this happen. So if I am going to write out my vector v in this basis, I have an x unit vector, I have a y unit vector, and I have a z unit vector, and I dot it with x. And this dot product distributes, and I get to pull out coefficients. Whatever other dot product we might cook up that is relevant to whatever functions we're working on, it's going to have to obey those rules. So if I do that, I have got the x part with x dot x. I've got the y part with x dot y. And I've got the z part with z dot x. And critically, x dot x gives us 1, x dot y, and x dot z gives us 0. So what's important about this is the fact that this is an orthonormal basis. It's normal because when I dot a vector to itself, I get 1. And it's orthogonal because if I dot different vectors together, I get 0. So if I want to be able to pull coordinates out to explain these functions, I'm going to need an orthonormal basis. I'm going to need some notion of taking a dot product for functions. So let's see what a helpful definition of a dot product for functions would be. If I just had to take my first guess at how I would dot product a function, I would approximate it by saying I'm going to work with the same line as before, But I'm going to make my function a finite list of finitely many points. A function is a list of infinitely many points. I can't write them out in one list step by step. They're continuous. But I'll just discretize it. I'll pretend that the function looks like this. So if I am dot producting two functions together, I am just going to sum them like I would vector coordinates. Make sure to complex conjugate f, whatever it's doing at one of my finitely many points, times g with whatever that's doing at one of finitely many points. But what we want is to take the limit as n goes to infinity, and what I have right there looks a whole lot like a Riemann sum. So the natural extension of this is to turn the sum over discrete points to an integral over continuous points. Over here with my dot product, I had to make sure I could pull out coefficients. I had to make sure I could distribute across things that were summed. Integrals do both of those things. Integrals are linear operators, and we can make inner products, or inner product is just a more abstract word for a dot product, out of integrals. So going back to Dirac notation, if I am integraling two functions together like this, I'm going to write it in Dirac notation the way we did before for dot products. So if you took quantum mechanics with the Griffiths textbook, you probably started with this notion, and this more matched what you had seen in electromagnetism before. That you have things, you integrate them together to see how well they overlap, and later you introduce this Dirac notation. But it's the same idea and the same notation all the way through. When you're dot producting vectors with finitely many elements in them, and you do the normal dot product, versus if your vectors are now these infinite dimensional things that have to be integrated together, it's all the same idea all the way through. However, we do not yet have an orthonormal basis. We still need an orthonormal basis, which I will write as ONB. And the best way to get an orthogonal basis is to get the eigenvectors of a Hermitian operator. So one of the exercises that Zach and I have given you for your homework, and something that we're going to talk about for the in-person sessions, are how to prove that all of the eigenvectors of a Hermitian operator are orthogonal to each other. That is one of the most essential things you need to know about them. So once we have a Hermitian operator and we find its eigenvectors, we're done. We've got an orthogonal basis, and that's really, really useful. Then we can just normalize each of our vectors, and we have an orthonormal basis. Now, I'm kind of doing a sleight of hand here where I'm assuming that once we find some Hermitian operator, then its eigenvectors are enough to build whatever we want. In a finite dimensional vector space, you can assume that, no problem. In an infinite dimensional vector space, that's a little bit dicier and takes a lot of analysis to prove properly. But here in physics, we just see that it works, and we trust that it works, and we know it just does its job. So we're going to need to look a little bit harder to find the right basis. If you throw out another basis, like the Taylor series basis, that is not going to work. These are not going to be orthogonal to each other under an integral. If I pick different polynomial powers and integrate those together, those are in general not going to be 0. So we're going to need to find a Hermitian operator, get its eigenvectors, and use that to construct our basis, so we can start doing linear algebra on functions.